So the last topic is to really bring back together a final vision of conservation of energy. So to do this, we have to now make our system not isolated. Previously, we said that isolated systems, energy is definitely conserved because you're only transforming it within our system. If we can't say that our system is isolated, so for instance, if there is an external agent doing work on the system, we can just think about this work explicitly. We have to do that now. And again, there are many choices that you can make for your system. And if you consider, for instance, the Earth as part of your system, gravity is an interaction within the system. But a person pulling on a rope, you might need to think about as an external agent. So we now have some sort of work that is being done on our system by an external agent, and this could actually be a decrease in energy. You can think about this as either an increase in system energy or a decrease in system energy, depending on what that interaction actually looks like. So our complete energy model is actually going to say now that we have our system that before we talked about it being isolated and only having transformation here. Now we actually have energy potentially entering and leaving. Now you don't have to worry about this separately. The idea being that it's just a question of sign. That if energy is leaving the system based on some force pulling energy effectively out of the system, then your work is negative. Otherwise, if work is being done on the system to increase its energy, which is usually more the case, you have positive work done. What this means is that the energy in your system can change. And so that change in energy is going to be equal to the external work done. If your system is isolated, no work is done, and that change in system energy is zero. At this point, we now have our complete model of conservation of energy. And these equations are really important. Now, obviously, you're going to have equation sheets whenever you need to do calculations. However, it really is a representation of a concept here. So the concept is the idea that we have our system and that there is energy in our system. That's here, right? So our system. And that it wouldn't change if the system is isolated. And so that means an isolated system has no external work done. If the system is not isolated, then you do have a change in your system energy. Now, this formulation of it is talking about changes in energy, and the idea being that even if this side of the equation is zero, that some of these might be increasing or decreasing due to transformations between these types of energy. We can rewrite this equation to be in terms of initial and final. Now, in doing so, we're not assuming that external work is zero. There was a previous version of this equation where we said the system was isolated. So if there's only one equation you're going to learn or understand, it should be one of these two. These are completely equivalent. It's just using the definition that delta equals final minus initial. And that's always been our definition of delta. So in this case, we have final minus initial, and then change in thermal energy, which we never break into pieces. So your change in thermal energy and your final have the same signs. So final, change in thermal energy. We then are subtracting off the initial, which we could then move to the other side of the equal sign as a positive value. So in a way, you can think about your before and you can think about your after. And so depending on what you actually know about your system, it might be easier to formulate it as the second equation rather than the first one. But this format tells you that before you had some initial energy and you have a change that the external environment is causing in your system. So afterwards, that change has happened, and you've potentially transformed some energy into thermal energy. So I like thinking of this as kind of before, because this is what's coming in. If it's energy leaving, then it's negative. And then you have final. So please have these be your starting point. These are the valid starting points for conservation of energy. If you know that your system is isolated, if you're going to model it that way, then you can set this equal to be zero. If you don't have friction, if your system is non-dispersive, that means mechanical energy is conserved, so that delta E thermal is zero, and it simplifies down to an earlier version of conservation of energy when we had initial kinetic plus initial potential equals final kinetic plus final potential. But this is the most general form. last thing is that we previously met the idea of energy bar charts when we were focusing on kinetic and potential. Now we can actually expand our energy bar charts to include external work done on the system and thermal energy. It is still true that the sum must be equal. And the reason for this is because we are now considering all energy that is in our system and or that is entering and leaving. So this is again where I like to think about this as kind of before and after. So if you look what we have up here, if we count each of these as say 1 joule of energy, we have 1, 0, 3. At the end we have 1, 2, 1. Our total system energy, right, is equal to 4 here, and it's equal to 4 here. So I don't want to write this as change in energy because it's really not it. We do have a change, that's this external, but we're saying here 4 equals 4, that's true. But in order for that to be true, we've had to account for the addition of energy to our system through an external force doing work, and the transformation of some of the kinetic and potential energy into thermal energy. So if you find the energy bar charts helpful, feel free to draw those as part of your representation of a problem, in that it can help you keep in mind all of the energies to think about.